In order for us to do real-world application problems involving the reciprocal function family, one of the things we're going to review is finding points of intersection between two rational functions. So I want to find the point of intersection of y equals 6 over x minus 2 and y equals 6. The way that it works is you put into y1 equals 6 divided by, and then you have to put the denominator in parentheses. Whenever you have an expression that means more than one term in the numerator or the denominator of a fraction, that expression needs to go in parentheses or the calculator will misinterpret what you're trying to type in. In y2 equals, you're going to put 6, and then you're going to graph. After the graph pops up, we have a function called intersection on the calculator that finds points of intersection for me, but there's something special we're going to have to do. So you're going to hit second trace, and then when you're back on the graph screen, after second trace you have to hit number 5. Alright, so now you're back on the graph screen, and it says first curve down at the bottom. Your cursor is probably on somewhere down here, or it's on that branch of the graph. Well, the point of intersection does not intersect with that branch of the graph. So you're going to have to get it to move over here. All you have to do is keep pressing the right arrow button until you see the cursor pop up on the branch over here. Once it pops up on the branch on the right hand side, then all you have to do is hit enter 3 times. And the point of intersection will pop up at the bottom of the screen. It should tell you 2.98 approximately, correctly rounded, 6.13. Let's try another one. Let's graph y equals 3 over x plus 1 and y equals negative 4 and find the point of intersection. Remember, when you plug this into y1 equals, you need to do 3 divided by parentheses x plus 1. And in y2 equals, you're going to put y equals negative 4. When I graphed this in my calculator, and it looks something like this, it's not quite like that. I should make it look, I think it looks more like this. Sorry. My cursor popped up here when I went to second trace. The problem is the point of intersection I'm looking for is down here on this branch. So I'm going to press the left arrow until my cursor pops up down here. Once my cursor pops up somewhere down there, then I will hit enter, enter, enter for the point of intersection to come up. The point of intersection comes up as negative 1.75, comma, negative 4. Now let's do a real-world application problem where we're going to have to find the point of intersection between two graphs. The rowing club is renting a 57-passenger bus for the day. The cost of the bus is $750. 5 passengers will be chaperones. If the students who attend share the bus cost equally, what function models the cost per student C with respect to the number of students N who attend? How many students must ride the bus to make the cost per student no more than $20? So the first thing we're going to do is we're going to talk about how do you find a function that models the cost per student C? Well, the cost per student is going to be the total cost of the bus divided by the number of students who attend, which at this moment in time I don't know how many people there are. Alright, now the second part is how many students must ride the bus for the cost per student to be no more than $20? Well, first of all, let's look at the domain of this function. Remember, the domain is what numbers can you plug in. Well, one of the reasons n can't be 0, other than the fact that it makes the function undefined, is that if no students go on the trip, would there actually be a trip? Well, of course not. Alright, so there's got to be at least one student going on the trip. What's the maximum number of students who can go on the trip? The bus holds 57 passengers, but of those 57 passengers, 5 of them have to be chaperones, right? So there aren't going to be 57 students. There could be up to 52 students. The reason I wanted to look at the domain is because when I go to graph this in my calculator, I'm going to change the window setting on my calculator. Alright, so this is what I'm going to do now. In order to find out how many students must ride the bus to make the cost per student no more than $20, if I use my graphing calculator, is I'm going to plot in y1 equals 750 divided by x, and in y2 equals, I'm going to graph 20. And what I'd like you to do now is I'd like you to go to your Windows setting. Under the Windows setting, make your x minimum 0, because I always like to make it just a little bit smaller than my minimum domain. And your x maximum, since our maximum in the domain is 52, how about I make it 60? The other thing that we'll need to change on our window is the y minimum and maximum, because one of the things we're graphing is y equals 20, but the default window setting, y only goes up to 10. So what I would do is I would change my y minimum to 0, because, you can't spend less than $0 on this bus trip. And then I would make my y maximum 30. Then hit graph, and you should see a decent graph. Once you get that decent graph, then go to second, trace, 5, enter, enter, enter. The point of intersection will be 37.5, comma 20. Well, here's the problem. You can't have 37.5 people. That does not include 37 people and Mrs. Friedlieb, because Mrs. Friedlieb is short. I do not consider myself half a person. So you have to figure out, which one is it? Is it 37 or is it 38? Which one is going to be less than $20? Well, another way we could have done this problem, instead of graphing it, we could have just plugged in 20 for C. So what I could have done was I could have done 20 is equal to 750 divided by n. This is just a proportion. How do you solve proportions? You cross multiply. So I would have found out this way, that it was 37.5. Well, then go back and plug in. What's 750 divided by 37? You're going to find out that the cost would be $20.27 a person. And then if you try $750 divided by 38 people, you're going to find out the cost would be $19.74. So it turns out that you would actually need 38 students to keep the cost at or below $20 per student. The last thing that I want to do in this particular video is talk about some other formats for writing these reciprocal functions. Sometimes you don't recognize that what you're working with is a reciprocal function until you rewrite it. Remember, in order to graph something in the graphing calculator, it has to say y equals. So we have to know how to solve these equations for y. Well, how do I get y all by itself? Well, since this is x times y, the inverse operation of times is divide. So you find out this is y equals 3 over x. When I graph that in the calculator, it's going to be two branches. The branches are going to be in quadrants 1 and 3. Remember, they're in 2 and 4 if it said negative 3 over x. Remember, the bigger we make the numerator of that equation, the further away from the origin the branches get. The asymptotes, the lines that the graph gets closer and closer to but never touches, are y equals 0, otherwise known as the x-axis, and x equals 0, which is the y-axis. If I solve this second equation for y, I get rid of the 5x by dividing both sides by 5x. Now, this is an interesting case because this is the case where the numerator is actually 0.4 because you have to take that 2/5 and change it into a decimal. We said that when the numerator of these direct or indirect inverse variation problems gets smaller, the branches actually get closer to the origin. So if I graph that one, again, it's going to be in quadrants 1 and 3, but it's going to be a little bit closer to the origin this time. And the asymptotes are still the x and y axes, because x cannot be 0, otherwise it's undefined. If x can't be 0, there's no y-intercept. Y can't be 0, because in order for y to equal 0, the numerator of that fraction would have to be 0. And the numerator is a constant, not a variable.